As we explore the various renewable energy options available to us, one resource that often receives less attention yet offers remarkable reliability is geothermal energy. Geothermal energy refers to the thermal energy extracted from the Earth's crust, a combination of heat left over from the planet's formation and the continuous heat produced by radioactive decay deep underground. Humans have been harnessing this natural source of warmth for centuries. From Paleolithic communities bathing in naturally heated hot springs to the Romans using geothermal warmth for space heating, the use of Earth's internal heat has a long and fascinating history. Electricity generation from geothermal sources, however, began only in the 20th century, marking a major milestone in renewable energy development. One of the greatest advantages of geothermal energy is its power stability. Unlike wind and solar energy, which depend heavily on weather and daylight conditions, geothermal systems provide a steady and uninterrupted supply of power. This makes geothermal an exceptionally reliable 24/7 energy source. Additionally, geothermal resources are abundant, especially near tectonic plate boundaries where heat access is easier. Because Earth's internal heat is continuously replenished, geothermal energy is considered renewable and sustainable over the long term. Economically, geothermal power has also gained an edge. Over the past few decades, power generation costs have fallen by nearly 25%. Modern geothermal plants can now produce electricity for about 5 cents per kilowatt hour, making them highly cost-effective. The global geothermal energy landscape reflects steady growth and diversification. By 2019, worldwide geothermal power capacity had reached approximately 13,900 megawatts. Beyond electricity generation, an additional 28 gigawatts of geothermal energy were being used for district heating, space heating, spas, industrial processing, desalination, and even agriculture. The sector also provided employment to around 100,000 people that same year, showing its broad economic impact. There are three main types of geothermal power plants. Dry steam plants use steam directly from underground reservoirs to drive turbines. Flash steam plants draw high-pressure hot water from the earth, converting it into steam to turn the turbines. Meanwhile, binary cycle plants transfer heat from geothermal water to another working fluid with a lower boiling point, allowing the turbine to operate even with moderate temperature geothermal sources. As of 2010, geothermal electricity was being produced in 26 countries, and by 2019, global installed geothermal capacity reached 15.4 gigawatts, with the United States alone contributing 3.68 gigawatts. Countries such as Iceland, El Salvador, Kenya, the Philippines, and New Zealand are leading examples of regions where geothermal energy plays a major role in national energy systems. From an environmental perspective, geothermal energy stands out as a remarkably clean option. It is renewable because the heat extraction rate is insignificant compared to Earth's total internal heat. Greenhouse gas emissions from geothermal power stations average around 45 grams of carbon dioxide per kilowatt hour, less than 5% of the emissions produced by coal-fired power plants. Its low emissions, constant availability, and long-term sustainability make geothermal energy a valuable part of the global renewable energy mix. With technological improvements and expanding capacity, geothermal energy is poised to contribute even more to global clean energy efforts in the coming decades. It is important to understand the role of thermal power in India's energy sector. Thermal power remains the largest contributor to India's electricity generation, a point frequently referenced in exams. Coal-based power plants dominate the thermal sector, supplying the majority of electricity across the country. In total, thermal energy accounts for about 75% of India's electricity production. Gas-based plants also support the grid by meeting peak hour demands, while diesel-based plants contribute only a very small fraction. Thermal power offers certain advantages. It is reliable, can consistently meet base load demand and has historically been more cost effective than many renewable sources. However, thermal power poses significant challenges as well. Coal dependency leads to severe environmental concerns due to high carbon emissions. These plants require large amounts of water for cooling, putting pressure on local resources. The sector's carbon footprint contributes heavily to pollution and climate change, pushing India to adopt cleaner and more sustainable energy alternatives. India is home to several massive thermal power stations. The Vindhyachal Super Thermal Power Station in Madhya Pradesh, producing 4,760 megawatts, is one of the largest. The Mundra Thermal Power Station in Gujarat follows with 4,620 megawatts. Odisha's Talcher Super Thermal Power Station generates around 3,000 megawatts, while the Sipat and Korba Thermal Power Stations in Chhattisgarh produce 2,980 megawatts and 2,600 megawatts respectively. These plants form the backbone of India's power generation infrastructure. To understand India's energy mix more clearly, we look at the breakdown of electricity production. Thermal power contributes roughly 75%, with coal alone accounting for around 55% of total generation, making it the largest single source of power. Gas-based plants add around 7%, while diesel plants contribute less than 1%. Renewable energy sources make up about 22% of electricity production. Solar and wind together contribute approximately 15%, and hydropower accounts for around 12%. Nuclear power, though small, provides a stable and consistent 3% of the national energy supply. This breakdown shows both the strength and the vulnerability of India's energy system. While thermal power is still dominant, its environmental impact and resource dependency highlight the urgent need for diversification. The rise of renewables, solar, wind, hydropower, and emerging technologies will play a crucial role in balancing India's energy demands with environmental sustainability. As we move deeper into renewable energy systems, one of the most versatile and widely used sources we come across is biomass energy. Biomass refers to organic material derived from plants and animals, anything from wood and crop residues to organic household waste and industrial byproducts. Today, wood and its residues remain the largest contributors to biomass energy, either burned directly or processed into pellet fuels and other forms. A variety of plants, including maize, switchgrass, miscanthus, and bamboo, can also be cultivated specifically for energy. One of the most important exam-tested concepts here is that biomass fuels can be carbon neutral because the amount of carbon dioxide they release upon combustion is roughly equal to the amount absorbed by the plant during its growth. However, it's equally important to remember that biomass has the lowest energy density per unit mass among major fuels, which affects its efficiency and transportability. Biomass energy is broad in scope because it utilizes different types of waste. Wood waste, such as leftovers from logging and wood processing, is widely used as a fuel source. Agricultural waste like straw provides another major input. Municipal solid waste, the organic fraction of household garbage, can also serve as a valuable energy resource. Even when solid waste is buried in landfills, it continues to produce methane-rich natural gas, which can be captured and burned for power. This fact is often highlighted in exams. Biomass also includes manufacturing waste, such as organic industrial residues. Given its diversity, biomass becomes a flexible renewable option that can turn everyday waste into usable energy. A particularly important category under biomass is energy crops, which are fast-growing, low-maintenance plants grown specifically for producing renewable fuels. These crops, known for their high calorific value, can be converted into gaseous or liquid fuels, another point emphasized in examinations. Because energy crops grow quickly and require minimal input, they have become valuable components of sustainable bioenergy production. Biomass must often be converted into a more efficient form before it can be used for energy, and several technologies help achieve this. The first is gasification, which produces what is known as producer gas. This gas is formed when solid biomass is converted into a combustible fuel mixture. Its heating value is largely determined by its hydrogen and methane content, making it suitable for use in internal combustion engines. Another method is pyrolysis, which transforms raw biomass into bio-oil, a liquid intermediate product that can replace heating oil. This process produces minimal waste and is frequently mentioned in exams. Biomass can also be upgraded into biodiesel, a renewable and biodegradable fuel produced from vegetable oils or animal fats. Biodiesel is an eco-friendly alternative to petroleum diesel, but one key difference to remember is that biodiesel has higher viscosity, which affects how it flows through engines. Finally, anaerobic digestion produces biogas, a renewable gaseous fuel derived from food and animal waste. Its calorific value depends on methane concentration, and with methane levels around 60%, biogas becomes highly energy-rich. A major theme surrounding biomass energy is its relationship with carbon neutrality. Energy generated from biomass is traditionally considered carbon neutral because the carbon released during combustion is offset by the carbon absorbed during plant growth. This is why carbon dioxide emissions from bioenergy are often excluded from emission inventories, and climate study calculations, a point frequently tested in exams. However, it is also important to acknowledge that biomass does add CO2 to the atmosphere when burned. It only remains carbon neutral if new biomass is continually grown to absorb it. Still, emissions from bioenergy are significantly lower than those produced by fossil fuel combustion. From an economic standpoint, biomass power stands out as one of the least expensive renewable power sources, a fact often highlighted in exam papers. Its low setup cost makes it attractive compared to wind or tidal power. But biomass also comes with challenges. The biggest obstacle is land requirement. Large amounts of land are needed to grow energy crops, making sustainable land use absolutely essential. Environmental concerns also arise in the form of eutrophication, when excess nutrients like nitrates and phosphates enter water bodies. Over time, this leads to algal blooms, oxygen depletion, poor water quality, and a decline in fish health. Finally, when discussing cleaner fuel options, it is worth noting how biomass compares to natural gas. Natural gas is considered one of the most eco-friendly fossil fuels because it produces fewer pollutants and emits less carbon dioxide per unit of energy than any other fossil fuel. As we move forward into another major energy resource, we come to nuclear power, a technology that generates electricity using nuclear reactions. Most of the world's nuclear electricity comes from nuclear fission, in which the atoms of uranium or plutonium split apart, releasing enormous amounts of heat energy. Nuclear energy can also arise from nuclear decay, which is used in specialized applications such as space probes, and research continues into nuclear fusion, the process that powers the sun, although fusion-based electricity is still not commercially achievable. Because of the sheer energy released during fission, nuclear power has become one of the most powerful and efficient energy systems available today. To understand how nuclear plants work, we start with the reactor core. Most nuclear power stations operate as thermal reactors using enriched uranium in what is known as a once-through fuel cycle. The most widely used fuel is uranium-235 or U-235 because its atoms split easily and release significant energy. As U-235 undergoes fission, the heat produced is used to convert water into steam, and this steam drives turbines to generate electricity. Plutonium-239 or Pu-239 may also be used in certain reactor types, but U-235 remains the preferred fuel due to its efficiency and reliability in maintaining a sustained chain reaction. Fuel inside a typical nuclear reactor operates for about 3 years before it becomes unable to sustain fission. Once removed, it is stored in spent fuel pools where it cools before being moved to long-term storage. This used fuel becomes high-level radioactive waste, requiring isolation for thousands of years, although advanced reactor designs such as fast reactors may eventually reduce this timescale. Some countries reprocess spent fuel to recover usable fissile materials. But reprocessing is expensive and carries proliferation risks due to the presence of plutonium. Nuclear power has evolved through decades of research, progress, and challenges. The first commercial nuclear power plant was built in the 1950s, initiating a rapid expansion. From the 1970s to the 1990s, nuclear capacity grew dramatically, reaching nearly 300 gigawatts worldwide by 1990. However, the sector faced major obstacles after two severe accidents: the 3 Mile Island accident in 1979 in Pennsylvania and the Chernobyl disaster in April 26, 1986 near Pripyat in the former Soviet Union. Both incidents brought nuclear safety into the global spotlight and significantly increased regulation. More recently, the Fukushima Daiichi accident on March 11, 2011, triggered by a massive earthquake and tsunami in Japan, once again raised concerns about disaster preparedness, safety systems, and public trust. Despite these challenges, nuclear power remains an important global energy source. By 2022, global nuclear capacity had reached around 390 gigawatts, supplying nearly 10% of the world's electricity. As of August 2023, there were approximately 410 civilian reactors operating worldwide, with many more under construction. The United States operates the largest nuclear fleet, producing almost 800 terawatt-hours of electricity per year with an exceptionally high capacity factor of 92%, a key indicator of reliability and efficiency. At the heart of nuclear energy is the fission process, a chain reaction in which neutrons released from one split nucleus go on to split additional nuclei. In reactors, this process is kept under control using moderators, often water, which slow down fast-moving neutrons to sustain the chain reaction safely. In fact, in water-cooled reactors, water acts both as the coolant and the moderator. Some reactors operate differently, such as breeder reactors, which are designed to produce more fissile material than they consume. Unlike traditional reactors that rely on the rarer U-235, breeder reactors can use uranium-238, which is far more abundant. India has ambitious plans for this advanced technology, with 6 fast breeder reactor units scheduled to become operational by 2039. The first 2 units are under development at Kalpakkam in Tamil Nadu. Nuclear power offers several compelling advantages. It has an extremely low fatality rate compared to coal, petroleum, natural gas, and even hydroelectricity. It also emits no greenhouse gases during electricity generation, making it one of the cleanest energy options available. Over its full life cycle, nuclear energy has lower carbon emissions than many common renewables. Its high capacity factor, averaging 89% globally, shows that nuclear plants operate at full power far more consistently than wind or solar installations. However, nuclear power faces significant challenges. Safety concerns continue due to the potential for accidents despite technological improvements. Long-term radioactive waste management remains a major issue, requiring secure storage for long durations. Finally, nuclear plants involve high construction costs and long timelines, making deployment slower than other emerging energy technologies. Even with these limitations, nuclear power remains a critical part of the global energy mix, reliable, low carbon, and capable of producing massive amounts of electricity with minimal emissions. With continued advances in safety, waste reduction, and reactor design, nuclear power is poised to remain a key player in ensuring energy security and combating climate change. As we shift our focus toward India's nuclear energy landscape, it becomes clear that nuclear power plays a significant, though still developing, role in the nation's electricity generation. In India, nuclear power stands as the 5th largest source of electricity, coming after coal, natural gas, hydropower and wind. As of November 2020, the country operates 23 nuclear reactors across 8 nuclear power plants with a total installed capacity of 7,380 megawatts. During the fiscal year 2020-21, these reactors collectively generated 43 terawatt-hours, accounting for just over 3% of India's total power production. While this percentage may seem small, nuclear energy provides stable, low-carbon electricity, which is crucial for a sustainable energy future. Moreover, India is actively expanding its nuclear capacity with 10 additional reactors totaling approximately 8,000 megawatts currently under construction. India has long envisioned a major expansion of nuclear energy. In October 2010, the government announced a target of 63 gigawatts of nuclear capacity by 2032. However, the Fukushima disaster of 2011 significantly altered the public perception of nuclear safety. Anti-nuclear protests intensified at several project sites, most notably the Geothermal nuclear power project in Maharashtra and the Kudankulam nuclear power plant in Tamil Nadu. Additional resistance emerged when the proposed nuclear plant near Haripur was denied permission by the West Bengal government. Concerns about safety and environmental impact ultimately reached the Supreme Court through a public interest litigation challenging aspects of India's civil nuclear program. India's nuclear plants have historically operated with relatively low capacity factors. The lifetime weighted energy availability factor as of 2021 stood at around 66%. Still, recent improvements are notable, with availability rising to over 74% between 2019 and 2021. Some of the earlier challenges stemmed from nuclear fuel shortages, but ongoing reforms in fuel procurement and reactor technology have begun to enhance operational efficiency. A significant milestone in India's nuclear program is its advancement in thorium-based fuel technologies. Unlike most countries that rely heavily on uranium, India possesses abundant thorium reserves. As part of its three-stage nuclear strategy, India aims to develop a prototype reactor capable of using thorium and low-enriched uranium, a step that could reshape the long-term sustainability of nuclear power in the country. India's network of nuclear power stations spans multiple states. Key operational plants include the Tarapur Atomic Power Station in Maharashtra, the Rajasthan Atomic Power Station, the Madras Atomic Power Station, and the Narora and Kakra power stations in Uttar Pradesh and Gujarat respectively. The Kaga generating station in Karnataka and the Kudankulam plant in Tamil Nadu further strengthen the grid. Meanwhile, the prototype fast breeder reactor at Kalpakkam, currently under construction, represents an important technological leap toward India's future breeder reactor fleet. Upcoming and proposed projects such as the Gorakhpur Haryana Anu Vidyut Pariyojana and the Jaitapur nuclear power project signal India's long-term commitment to nuclear energy despite public debates and regulatory scrutiny. On December 5, 2025, India-Russia nuclear cooperation marked another major milestone when Russia's state-owned nuclear corporation Rosatom delivered the first consignment of nuclear fuel for the initial loading of Kudankulam nuclear power plant's Unit 3 inches Tamil Nadu. The delivery coincided with President Vladimir Putin's visit to New Delhi, highlighting the strategic importance of the partnership. The fuel assemblies, produced by the Novosibirsk Chemical Concentrates plant, arrived via a cargo flight operated by Rosatom's nuclear fuel division. In total, 7 shipments from Russia are planned to supply the full reactor core and reserve fuel under a 2024 contract, which guarantees lifetime fuel supply for both the 3rd and 4th VVER 1000 reactors. With 6 reactors planned and a total capacity of 6,000 megawatts, Kudankulam remains India's largest and most significant nuclear power project, symbolizing deep and ongoing Indo-Russian collaboration in the nuclear energy sector. Now, shifting from nuclear energy to a more ecological and land-based renewable resource, we explore energy forestry, which focuses on growing fast-growing trees and shrubs specifically for biomass-based energy production. These plantations are designed not for timber or traditional forestry uses, but for producing biofuels, heating fuel, and biomass for power generation. Energy forestry typically follows two major systems: short rotation, coppice or simply SRC, and short rotation forestry or SRF. In SRC, species such as poplar, willow, and eucalyptus are harvested every 2 to 5 years. In SRF, species including alder, ash, birch, sycamore, poplar, and eucalyptus grow for longer cycles, typically 8 to 20 years before harvest. Both systems allow predictable fuel supply while matching ecological conditions and energy requirements. One of the biggest advantages of energy forestry is its role in supporting carbon neutrality. Trees absorb nearly the same amount of carbon dioxide during their growth as they release when burned, making them significantly more sustainable than fossil fuels. In addition, wood offers a highly efficient bioenergy source. It provides substantial energy relative to the carbon emitted. Another benefit is that trees do not require annual harvesting. Their growth cycles can be extended or delayed depending on fuel demand and market conditions, giving energy forestry remarkable flexibility. The versatility of wood-based biomass is also an asset, as different forms of wood products can be used in multiple energy applications. Energy forestry also provides several critical environmental benefits. Tree plantations help stabilize riverbanks and reduce soil erosion, a process known as bank stabilization. Through phytoremediation, certain species have the ability to clean contaminated soil, improving soil health over time. Experiments in Sweden, for instance, have shown that willow plantations enhance water quality compared to conventional agricultural practices. When integrated thoughtfully into landscapes, energy forests can enhance biodiversity, improve pollination, reduce flood risks, and meet bioenergy demands simultaneously. This kind of multifunctional resource system aligns well with sustainable land management goals. From a productivity standpoint, energy forestry shows promising results. Under optimal conditions, yields can reach up to 11 oven-dry tons per hectare annually. While actual yields in commercial plantations, such as those in Scandinavia, may be lower due to climate variability, energy forestry remains a highly productive and environmentally supportive alternative to fossil fuels. With rising global demand for sustainable energy and carbon-neutral solutions, energy forestry offers countries an innovative pathway to meet bioenergy needs while restoring ecosystems and improving environmental health.